Today's videos are about collision avoidance. The collision avoidance problem is very similar to the path planning problem. Remember that in path planning, our goal was to traverse a path between a start point and an end point defined in the Cartesian coordinate system. What we did in path planning was we specified an equation for the path that we want to follow, for example, a half circle. We then transformed points from the Cartesian coordinate system over to the configuration space in order to make sure that all of the points along our desired path fell within the workspace. In the collision avoidance problem, we're going to introduce a little bit of a complexity. In this problem, we're going to imagine that we have some kind of an obstacle in the Cartesian coordinate system, and we know where that obstacle is. So, for example, I'm going to imagine that we have a box. Here I've drawn a box in my Cartesian coordinate system between points A and B. Let's say this is point A and this is point B. Now, I want to find a path for my manipulator to take between points A and B that allow it to not collide with the box in the Cartesian coordinate system. So, in this problem, I'm not going to assume that I know ahead of time that the path should be a half circle or the path should be a parabola or something like that. I just want to find some path between A and B that allows my manipulator to not collide with the object in the space. This is a problem that on the surface seems like it should be an easy problem because people do this without even thinking about it. We have no trouble figuring out how to get from point A to point B without colliding with objects that are in our path. But it turns out that this problem in robotics is actually quite a difficult problem. So I'm going to show you some of the rules of thumb or methods that we use to solve this problem, but we don't really know an optimal solution. The approximate solutions or rule of thumb solutions that we use are similar to the way that we plan motions when we don't have things to collide with. In other words, we're going to start by transforming things from the Cartesian coordinate system over to configuration space. I'm going to show you how we do this by setting up an easier problem than the one I've shown you here and walking you through how we solve the easier problem. I'm going to give you an example of how we do collision avoidance using the example of this 2-link, 2 degree of freedom planar manipulator that I've used for examples in the past. In the simple path planning problem that we saw previously, we had a situation where we had a target pick point and a target place point, or in other words, a target point, 2 target points that we wanted the end effector to move between. And we also had a target path that we wanted the end effector to use, for example, a half circle between these 2 points. And we learned how to figure out how to move the end effector from one point to the target point through the path that we specify. Today, for the collision avoidance problem, I'm going to introduce a new element of complexity. Let's suppose that there is an object in between these 2 points, or in fact anywhere in the manipulator workspace, that we don't want to collide with. And I'm using my calculator as an example. In this kind of a problem, we want to move the end effector between our 2 target points, but we want to do it without colliding with the object in between. Now, if we were just doing this on our own, not trying to calculate it, we can see what the solution would be. We might move the manipulator all the way around the obstacle and come into the target point from the other side, like that. The question is, how do we find this kind of a solution automatically without having to do it ourselves? This kind of a problem becomes an issue when the locations of obstacles are more complex. We may have many obstacles within the workspace, or perhaps our manipulator is more complex than this simple one sitting here. So how do we solve a problem like this? Now, although this problem seems like a simple one because human brains are able to solve a problem like this without too much difficulty, actually, this is a conceptually very difficult problem to solve. And it's a problem that's been studied by computer scientists for quite a while. So the solution that we're going to learn today is a solution that becomes very complex as our manipulator becomes more complex. And it may not be the optimal solution, it's only an approximate solution. The solution to the collision avoidance problem has 2 steps. Step number 1 is to transform all of the obstacles that we have in our Cartesian space over to configuration space. Once we have the obstacles in our configuration space, step 2 is to find a path between our start and end points that does not go through the obstacles that we now have in configuration space. Actually, each of these steps has its own challenges. I'm going to start by showing you how we do step 1. Step 1 is to transform the obstacle, our calculator here, from Cartesian space, which is what you're seeing here, to configuration space. So the first thing I'm going to do is draw the configuration space. In this case, my configuration space has only 2 dimensions because I have only 2 joints, theta 1 and theta 2. I'll now go and check what is the range of motion that each of these joints can go through. When I check the workspace of my manipulator, I ignore for the moment my start and end points, and I ignore any obstacles in the space. I first rotate joint 1 all the way through its motion, and I see that joint 1 can move between 0 and 360 degrees. I then check joint 2 by itself, and I move it through its full range of motion. Joint 2 can move through 360 degrees, just like joint 1 can. Back in configuration space, I'm going to mark my workspace. I need to show 0 to 360 degrees in both of the axes, so I'm going to draw my axes in a little bit better position. Zero to 360 in theta 1 and 0 to 360 in theta 2. And so this box marks my workspace. I'll just draw an arrow to the inside, showing that the inside of this square is the workspace. Next, I need to mark my start and end points in configuration space. To do that, I'll go back to my model. I'll find the start and end points in configuration space by using inverse kinematics. I'll take the XY position of the start point and find the theta 1, theta 2 that gets the end effector in that location. And I do that using the inverse kinematics equations. I then go find the angles theta 1, theta 2 that place the end effector at the end location, also using inverse kinematics, and I'll mark those points on my configuration space. Using my inverse kinematics, I find out that the start point is at theta 1 equals 310 and theta 2 equals 110. There is my start point in configuration space. Note that when you use the inverse kinematics to calculate the start and end points in configuration space, there is likely to be more than one solution. These two solutions are known as elbow up and elbow down configurations. For example, the end effector can go to the start location either in this configuration, or I have to ignore my obstacle here. That will come into play in a moment. Or the end effector can reach the start point in this configuration. Before I go through the step checking for collisions with the obstacle, I won't know which of these positions I would rather have. So I'm going to mark both solutions to the inverse kinematics in my configuration space. Back here in configuration space, I'm going to mark this point as start point 1. That's the first possibility for how to place the end effector at the start location. The second option is at theta 1 equals 45 and theta 2 equals 270. I'm going to mark this point as start 2. These are two possibilities for how the end effector can reach the start point. I'll now go through the same process to find the 2 points in configuration space that allow the end effector to reach the end point. Using the inverse kinematics, I find that the two possible solutions for the end effector to reach the end point are approximately 110 for theta 1 and 270 for theta 2. That's end possibility 1. The other possibility is at about 10 degrees for theta 1 and 110 for theta 2. This is end possibility 2. My goal here is to find a path between one of the two start points and one of the two end points that does not allow the manipulator to collide with the obstacle. So the next thing that I have to do here is to draw the obstacle, not in Cartesian space where it is right now, but in this configuration space. Here's how we do that. I'm going to put my obstacle back in its location, and we will find out how to draw the location of this calculator in configuration space. The first thing I'm going to do is I'm going to ignore the second link of my manipulator. In order to let me ignore it, I'm going to just fold it down along the first link so that I can move the first link independently. I'm going to move this link until it collides with the calculator. Now this is how we do it when I'm doing it physically by hand. When we're drawing it out on paper, what we can do is find what angle this line, if we represent this first link as a line, what angle is this line at when it intersects with the corner of this calculator. For now, what I'm going to do is I'm going to move the link until it collides with the calculator, and I'm going to record what angle that is. Here, that angle is about theta 1 equals 5 degrees. Then I'm going to move the link to the other side of the obstacle and check what angle it's at when it collides with the obstacle on the other side. Here it's at about 45 degrees. This tells us that the manipulator will collide with the obstacle anywhere between 5 and 45 degrees, regardless of the angle of theta 2. So let's go draw that in configuration space. I'm going to draw the obstacle in red on this plot. We found that the end effector, the manipulator, would collide with the obstacle anywhere between approximately 5 degrees and 45 degrees. And that is a collision regardless of the value of theta 2. So this entire inside of this rectangle is a collision. This tells us that we should not use end point 2, and we should not use start point 2. But start 1 and end 1 are still within the range of possible places that are both within the workspace and not a collision. Now we have to go back and account for the second joint and the second link. Unfortunately, adding the second link to our collision problem is quite a bit more complicated than accounting for only one link. In fact, as you add more links to the manipulator, the collision avoidance problem becomes exponentially more difficult. Here's how we account for the second link. I know that the second link moves in a circle around the joint axis. So I'm going to imagine that there's a circle drawn around this center point, and I'm going to move the first joint until that circle intersects with any point of my obstacle. And that would happen approximately as I've shown here. I'm going to take note of what is the theta 1 angle at which the second link first makes contact with the obstacle. This angle is approximately 330 degrees. I'm going to right away go and mark that in my configuration space. At around 330 degrees, we have what I'm going to refer to as a danger zone. This danger zone falls to the right, or the higher angled degrees of 330. This danger zone does not mean that in this zone we are guaranteed to collide with the object, just that there's a possibility that the object will be collided with. So I'm not going to hash it off the way I did over here with a guaranteed collision. For now, I'm just going to mark it as a danger zone. I need to do the same thing on the other side as well. I'm going to move this manipulator around and find out at what angle the second link first makes contact with the obstacle on the other side. This angle is approximately 80 degrees, and the danger zone is less than 80 degrees. When the joint number 1 is less than 80 degrees, there's a possibility that the second link will collide with the obstacle. I'm going to go mark that in my configuration space as well. 80 degrees is around here. So I'm going to mark a little arrow here and say that this is another danger zone. Now I can see that my start and end 1 points do not fall either in the guaranteed collision area or in either of these danger zones. This makes this example problem much easier. If there are no other collisions that I have to worry about, we could move from start point 1 to end point 1 in a straight line in configuration space. Or I could plot a different path in Cartesian space, transform that path into this configuration space, and check to see if the points in the Cartesian path fall within the guaranteed collision zone or within the danger zone. Now, sometimes it will happen that your start and end points, or perhaps a point along the path that you want to take between start point and end point, will in fact fall within the danger zone. In that case, we have to be much more specific about which points within the danger zone are actual collisions and which are not. I'm going to show you an example of how we do that. If it happens that one or more of the points that we want the end effector to go to or through fall within the danger zone, I have to be more specific about which points in the danger zone are actual collisions. The way we do that is by placing the end effector at each of the points along the outside of the object that is the obstacle. And for each of these points where the end effector collides with a point on the perimeter of the obstacle, I'll plot those theta 1 and theta 2 points in my configuration space. So this is another example here where the end effector is touching the top edge of the obstacle, or on the bottom here where the end effector touches the edge of the obstacle down here. I'll find each of these theta 1, theta 2 coordinates and plot them on my configuration space, once again by using the inverse kinematics. In configuration space, those collisions will look something like this. At the far end of the collision, when the danger zone just begins, there's only one value for theta 2 at which this collision will take place. For example, I think in our example, it would look like this. It'd have 1 point in theta 2 that collides with the object. As theta 1 moves closer to the object, the range of bad theta 2's will expand. So the actual collision zone will expand to something like this. And this actual calculation is a little bit tedious. We'll do an example in class where we write a program to automatically calculate these points. When I'm doing it like this by hand, this is just to give us a feel of how much additional calculations are actually necessary. For example, if I find that my start and end points, as in this example, are not in either a collision area or a danger zone, I can stop and I don't have to do all of the additional calculations. On the other side, in the danger zone, the actual collision space will also look something like this. Only a single angle of theta 2 is bad right where the danger zone begins, But as theta 1 becomes closer and closer to the actual collision zone, the bad theta 2's expand. Once we've found this map showing all of the collision areas and the danger zones, and finding our start and end points that are outside of the collisions, this is when we move on to step 2 of the problem. Remember that step 1 of collision avoidance was to transform obstacles from Cartesian space to configuration space. That's what I did in finding the collision space and also finding what I'm referring to as the danger zone, areas which may or may not contain a collision zone or a collision space. Step 2 then is to find a path between the start and end points that go around the obstacles in configuration space. I'm going to now show you an example where we do part 2. Let's suppose that you've drawn your configuration space as shown here. And let's suppose that you've found the workspace to be the same as the workspace that we did in this last example. So that the workspace is between 0 and 360 in both theta 1 and theta 2. So we have our configuration space, and within that configuration space, we've found the workspace. The next thing we want to do is find the collision space, the subset of the workspace which results in a collision. Suppose that you've found the collision space and it looks something like this. I'll call this the collision space. And suppose that your start point is here and your end point is here. How can we find a path from the start point to the end point that does not go through collision space? We want to find the shortest or most optimal path between start and end that does not go through collision space. This, in general, is a very difficult problem that requires a lot of computation to solve. And so roboticists have come up with a shorthand or approximate solution that tends to do a good job, and it's kind of a surprising solution. The solution to this problem that robotics engineers have come up with is something called the potential fields method. In the potential fields method, we're going to treat the end effector as though it is being attracted and repulsed by different elements within this configuration space. The end point is going to serve as an attractive force to the end effector. And every bit of collision space is going to act as a repulsive force. The strength of the repulsion or the attraction will be a function of the distance between the attracting or repulsing element and the end effector, which we will regard here as being a point in configuration space. In other words, the force on the end effector due to any attracting or repulsing element I will be equal to Ri. Ri is the distance between the end effector and the attracting or repulsing element. times a constant, which I will write here as a weight W. Note that the force is a vector, and so is Ri, which I shouldn't have called distance. I should really have called that the displacement. At each element of time, we take the forces on the end effector that are due to the end point and each element of collision space, and we add up the sum of all of these forces. The resultant force tells us which direction the end effector should move in. For example, let's use this example configuration space that I drew up here. I'm going to take this collision space and I'm going to divide it up into elements. I'm trying to make these elements all the same size, but drawing that is a bit difficult. I intend for all of these elements to be the same size. Each of these squares of collision space will exert a force on the end effector in the direction between the center of the element and the end effector. And the strength of that force is equal to the vector between the 2 points times W, a weight. So these two elements of collision space, which are very close to the end effector at the start point, will exert a large repulsive force. As we get farther away, the force exerted on the end effector by each of these elements of collision space will become smaller as the elements are farther away. Finally, we have an attractive force coming from the end point. In general, we have to make the weight on the attractive force from the end point larger than the repulsive forces from the collision space, since there are many more elements of collision space than the one single end point. So this end point will exert a large attractive force on the end effector. We break up each of these forces into their theta 1 and theta 2 components, and that gives us a resultant force on the end effector. The end effector will move in the direction of the resultant force. This is a thing that's very difficult to calculate by hand because there are many elements to add together. When we do the lab in class, we will be doing an example of a path planning problem using potential fields.